Electrochemical batteries. Okay. So first we're going to put half cells in an electrochemical battery on the reduction or the cathode or the positive pole, or on the oxidation, which is the anode or the negative side. Watch out when you use the E node, ox على red couple, and when you use the E of each couple. Remember, the E is for the corrected standard reduction potential using the Nernst equation. Getting reduction potential when the cell is under non-standard condition and finding the potential of the cell using the Nernst. We need to get the overall reaction in the cell and finding the EMF, which is the delta E or E of the cell, which is E reduction minus E at oxidation. Finding free energy, which is minus NF delta E. Finding equilibrium constant, which remember equilibrium constant only depends on E naught, even if it's non-standard. So it's log K equals N E naught divided by 0.592. This is when you're at equilibrium, this is the concentration of all the constituents are at equilibrium and the current stops, or the current flow stops. Electrochemical batteries and two half cells. Consider a half cell A and B. A is composed of a silver blade immersed in a solution containing ions of Ag plus at a concentration of 0.05. B is assembled by dipping a platinum plate or inert metal into a solution containing tellurium and tellurium 3 plus, whose concentration is these two values respectively. When the circuit is closed, the EMF of the battery, EMF, the silver electrode is the negative pole of the battery. Okay. Draw the scheme and write down the equation of the overall, and they gave you the E naughts. But they didn't give me the E naught of tellurium. They're asking for the E naught of tellurium, but they gave me the E naught of Ag. Now, typically, guys, if you were given the two E nodes, always with a battery, even if you're non-standard, choose the higher E node to be at the oxidation half, okay? And the lower E node to be at the reduction half, okay? مع إنه the E naught should be corrected to an E with different concentrations, but من هلا I'll tell you that there isn't that much of a difference. Calculate the K at equilibrium. Drawing the scheme. So we have this scheme, oxidation half at the negative pole, reduction half at the positive pole. And they said that the negative pole, we have my Ag, so the Ag is at the oxidation end. We still put the metal Ag in a solution of Ag plus. On the positive half, we will put a platinum plate. Why? Because the tellurium doesn't have a metal here. We have tellurium 3 plus and 2 plus. They're both liquids, and they're both be in a solution. So we use a platinum. They told me the E of the battery is 0.54, so that's on top. And so when they tell you that it is at the negative pole, that means it's at the anode. So if I want to draw it in a cell diagram, I will put the Ag separated at the anode, okay? And so it's going to, and the tellurium on the other side. Always the platinum, put him on the end. Remember, we have to separate the two liquids from a solid by a line. And the tellurium ما بتفرق إذا بتحطوا البلس أو ال 3 بلس قبل، ما عم بيفرقوهم بالمرة، مع إنه it's better to write it the way that the equation is written. So how is the equation written? So we have here, we have the oxidation half reaction. So Ag plus oxidation is loss of electrons. So becoming Ag plus 1 electron. So indeed the Ag solid is on this end, and the Ag plus with its concentration will be after the line. In terms of tellurium, what's happening? Reduction is going on this side. So gain of electrons. So we have tellurium 3 plus 2 electrons here goes to tellurium plus. Okay, so we have the T3 plus goes to T plus. Okay. That's how it's written. Always leave the platinum at the end. Notice typically the solids are at the end side of a ox red cell diagram. You always have your oxidation half, reduction half on this side. Then so we draw the scheme. Okay, the direction of electron flow and the conventional direction of the current. Well, the electrons always flow from the oxidation to the reduction, or from the negative plate to the negative pole to the positive pole. Here, you will always put the electrons from the negative, so you put like that. Okay, that's what we mean. So that if you just do like this, خلاص هاي اللي بتكون in terms of the cell diagram. This is the electron flow. The current always flows in the opposite of the electron flow. So the current is opposite. So you put it on the opposite side and you write I for current. Okay, electron flow, current flow. I need to read this for you. The direction of an electrical current is by convention the direction in which the positive charge would flow from a positive terminal to a negative terminal. Yani opposite to electron flow. If I had a positive charge, the positive charge will go to the negative pole. Okay, that's what a current means. Write down the overall equation. So we have tellurium, I already wrote it before, and the Ag half reaction is the oxidation half. So I write it in terms of oxidation, and the overall reaction, I must multiply the Ag by 2 to cancel the electrons, and you add the two equations. Okay, next. Knowing that E naught is that, what is the E naught of tellurium? Well, you have the E of the reaction total. Okay. You have the E of the reaction. That's what they gave you. So, and I need the E naught of the Ag, of the tellurium. Well, using Nernst equation of the overall reaction, we have E naught of the cell minus 0.0592 divided by total number of electron transferred log of products divided by reactants, because I left it in the negative, so products divided by reactants. H to its stoichiometry. Now, get the E naught of the cell on one side, get E of the cell on the other, or take all of this to the other side, and substitute the concentration of the different species at any time. Yani whatever they gave you initially, fine, put initially, because this is log of Q. Okay, at any concentration. And when I substitute that, I will get the E naught of the cell. And now you have the E naught of the cell. E naught of the cell is E cathode minus E anode. okay, or E negative pole, positive pole. They already told you that the negative pole is your Ag. So now you're able to find the E naught of the tellurium. Yeah. This is one of the ways. So E naught of the tellurium is, so I had to go and find the E naught of the cell to get the E naught of the tellurium first. Okay, watch out for these types of questions. So we're using the overall Nernst equation for the overall reaction to eventually get this E naught of the cell. And if I have the E naught of one of the couples, I can get the other. Calculate the equilibrium constant. Well, great. We already calculated the E naught of the cell in the previous question, so I just have to substitute. 2 is the total number of electron transferred times the E naught of the cell divided by 0.592. Remember, I could not have calculated this K before. I needed to get the E naught of the tellurium, or I need to get the concentrations at equilibrium. So if they gave me concentrations at equilibrium, I could get the K and then get the delta E naught. That's another way, which we did before. When you solve it, you get that the K reaction is complete. Remember, this N is the total number of electrons transferred in the overall reaction, not for any one half in particular. Well, I'm going to stop here and we will continue again. It's best that you guys try these on your own. First, we're on number 14. But we will continue next time with just Friday. The rest, pretty much whatever we can of the TD. Okay. Any questions?